Hi everyone, this is video number 3 of the Regents chemistry curriculum. In this video you're going to compare the properties of different elements and determine which one would be most useful for whatever purposes you're using it for. Let's get started. Here are some questions that you should be able to answer at the end of the video. Pause the video now, see if you know the answers to these questions. There are a few more. All right, let's get started. So, periodic table trends and atomic radii. The periodic table is arranged into periods and groups. All right, so let's see what this means. Explain that. Here's the periodic table. Like you just read, it is organized in periods and groups. So there's a total of 7 periods on the periodic table. Here's period number 1, left to right. 2, 3, 4, 5, 6, including this. These are the lanthanides. And 7, including this. These are the actinides. So these are the 7 periods of the periodic table. Now you have the groups. Here are the groups. 1, up and down, 2, 3, 4, 5, 6, 7, 8, 9. There are a total of 18 groups on the periodic table. All right. Now, the types of elements. Before we go on to this, actually, the atom number. The atom number on the periodic table is the number of protons that are inside the nucleus of that atom. So for example, hydrogen is number 1. There's only 1 proton inside the nucleus of hydrogen. Helium number 2, 3, 4, 5, 6, 7, and so on. The periodic table is arranged according to the increasing of the atom numbers. It goes from 1 all the way down to, or all the way up to 118. Okay, now, the types of elements on the periodic table. It's very important to point out the staircase here. Above and below the staircase, except aluminum and polonium. Above and below, above and below, above and below. Above, forget polonium. These are metalloids, which are simply elements that have characteristics of both nonmetals, everything to their left side, and metals, everything to their right side. I'm sorry, I flipped it. Nonmetals, everything to their right side, and metals, everything to their left side. So, again, these are all metals. All of these metals. Right side, these are all nonmetals. Okay, it's very important for us to know that hydrogen actually behaves like a nonmetal. All right, now you also have a fourth type of elements, which are the radioactive elements. These are elements number 83 and above. These are all radioactive. The reason why they're radioactive is because the number of protons inside their nucleus does not equal the number of neutrons. So when protons do not equal neutrons, we have a radioactive element or radioactive isotope. Okay? When we talk about atomic structure, we'll talk more in details about where the protons are, what their masses are, and so on. Okay. Let's continue reading. Okay. So based on what we read, we see that we are talking about chemical properties. Okay. In relationship to the number of valence electrons, we also see that we're talking about atomic radius, the trend across a period, and the trend down a group. Let's explain that. So, what are valence electrons? Valence electrons are the electrons that are at the end of the electron configuration. So here is the electron configuration. It's usually written at the bottom of the symbol. So for example, lithium has this electron configuration, 2-1. And if you add these together, you'll get the total of the number of electrons, which in this case is 3. Sodium, also known as natrium, hence the symbol Na, has 11 electrons, and they are arranged as follows: 2-8-1. That means there will be 2 electrons in the first shell. So if this was the nucleus, there will be 2 electrons in the first shell surrounding the nucleus. There will be 8 electrons in the second shell surrounding the nucleus. And there will be 1 electron in the third shell surrounding the nucleus. The number of valence electrons are the number of electrons that are present in the last shell. If this number for 2 elements is the same, then those 2 elements will react similarly. And what I mean by that, I mean that metals like to lose electrons and nonmetals like to gain electrons. Why do metals like to lose and why do nonmetals like to gain? Because they want to achieve what we call chemical stability. Now let's be clear. All the elements on the periodic table are electrically neutral. That means the number of protons equal the number of electrons. When metals lose electrons, they lose that negative charge. Electrons are negative, protons are positive, hence why they're neutral. Now if metals lose electrons, they lose that negative charge and they become more positive. So let's take a look. For example, lithium. Lithium has 3 electrons. If it has 3 electrons, it has 3 negative charges, Therefore, it must have 3 positive protons. If lithium loses a single electron, in this case, the valence electron that it has, it will have only 2 negative charges, but it will still have the 3 positive protons. In this case, you'll do the math, you find out that the overall charge will be +1. So 2 negatives, a negative. If you initially had a negative, a negative, a negative, 3 negative charges, and a positive, a positive, a positive, 3 positive charges, and you lost one of those negatives, now this negative will cancel out with this positive, this negative will cancel out with this positive, and you'll only be left over with this positive 1 charge, hence the charge of this lithium ion, +1. Okay, again, the reason why it wants to lose that valence electron that it has and form a +1 ion is because it wants to achieve chemical stability. For lithium, chemical stability means only 2 electrons in its last shell. Beryllium, same thing, 2 electrons in the last shell, or in the first shell. So chemical stability is simply 2 electrons in the first shell, in shell number 1, or 8 electrons in shell number 2, 3, 4, etc. If you have 8 electrons, you have what we call an octet, and an octet means chemical stability. If you have 2 electrons in your first shell, then you also have chemical stability. All right. With that said, let's talk about the atomic radius. All right. Down a group. First thing first, we should understand that the period number is the number of electron shells that you have. So if you're in period 1, every element in period 1 only will have 1 electron shell. Notice there's only 1 electron shell here. In this electron shell there are 2 electrons, which means helium is already chemically stable. In this electron shell there's only 1 electron, which means hydrogen is not yet stable and needs to either lose or gain or share its electron with another element. We'll talk more about sharing and transferring electrons when we get to bonding. So, period number 2 has 2 electron shells. Period 3 has 3 electron shells. So if I was to draw this, period 1, here's the nucleus, there's 1 electron shell. Period 2, here's the nucleus, 2 electron shells. Period 3, nucleus, 3 electron shells. And when I get to period 6, nucleus, notice how the radius tends to increase. The radius is the distance between the nucleus and the outermost shell. So here, 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 and then here. The radius is increasing because the number of electron shells increases down a group. Now, let's think across the period. Excuse me. Across a period, the number of electron shells remain constant. Notice, if you're in period 4, every element in period 4 will have 4 electron shells. But the number of protons, the positive protons that we talked about earlier, that are present in the nucleus, tends to increase. So in potassium, you have 19 protons attracting 4 electron shells. In titanium, you have 22 protons, 22 positive protons attracting the same 4 negative electron shells. If we get to zinc, we have 30 positive protons attracting the same negative electron shells. So more positive protons means more attraction power. So if this nucleus has a lot of positives, those electrons, the more positives we get, the closer and closer those electron shells will get to the nucleus. Hence why, going across a period, the radius of an atom tends to slowly decrease. All right. It's very important now, since we already talked about chemical stability, it's very important now to notice that noble gases are very chemically stable. That means they don't react with other elements, or they very rarely react with other elements. Notice helium has 2 valence electrons in its first shell. It's chemically stable. Neon has 8 valence electrons in its last shell. Argon, 8. Krypton, 8. All of these other ones also 8 valence electrons in their last shells. This means that they are chemically stable, and they will not, or they will very rarely react with all these other elements. So they don't want to lose electrons, they don't want to gain electrons, because they already have achieved chemical stability. Okay. Going back. Properties of elements. As we discussed earlier, 4 types of elements: metals, nonmetals, metalloids, and radioactive elements. We're not going to talk much about radioactive elements until we get to nuclear chemistry, but today we're going to talk about the properties of metals, nonmetals, and metalloids. Okay, metals. Main properties. Let's just discuss this first. This means that they melt at a very high temperature, meaning they change from solid to liquid, and they boil at a very high temperature, meaning they change from liquid to gas at a very high temperature. If you want to see the melting points and the boiling points of these elements, you can look at table S. Sorry, this is sideways, so you'll have to turn your screen, or you have to print table S, or print the reference tables from Google. Just type in Regents Chemistry, reference tables, and you'll get everything. So here, the elements, their symbols, their names, their melting points, their boiling points, their densities, and their atomic radius. So if I was to look at, for example, let's say aluminum, I know my window frames are made of aluminum. Notice aluminum will melt at 933 degrees Kelvin. Kelvin is a unit that we use to measure temperature. Boiling point, 2792. That means aluminum can boil at 2792 degrees Kelvin. Okay? Alright, so again, Kelvin. If you want to convert Kelvin to Celsius, you can look at the table T. There's a formula for you. Temperature. If you want to convert Kelvin to Celsius, Kelvin equals to Celsius plus 273. And if you want to know more about different units, here they are. In table D. To measure length, we use meter. To measure mass, we use grams, pressure, Pascal, and so on. Okay. Very important that we know the main phases of the elements at standard conditions. So here, what are standard conditions? Standard conditions, STP. STP stands for standard temperature, T for temperature, and P for pressure. Standard temperature and standard pressure, here they are on table A. We usually use 1 atmosphere, and we usually use 0 degrees Celsius. However, you may have to sometimes use 273 Kelvin, and you may have to sometimes use 101.3 kilopascals. So these are the standard conditions. At standard conditions, most of the elements are solids. However, mercury, right here, is the only liquid metal at standard temperature and standard pressure. Mercury used to be used in thermometers, no more. And bromine is the only liquid non-metal at standard temperature and standard pressure. Okay? Now, if you want to remember all the gases that are, or the elements that are present as gases at standard temperature and standard pressure, you remember that hydrogen likes to have FON, F-O-N, with chlorine and group 18. All of these elements are gases at standard temperature and standard pressure. The rest of the elements are solids, with the exception, obviously, of mercury and bromine. Okay, going back to properties of the elements. So because metals are mostly solids, they have strong intermolecular forces. We talked about this. They don't dissolve in water. You cannot grab a piece of aluminum and expect that it will dissolve in water. If you put a piece of aluminum in water, it will remain as a piece of aluminum. Okay. Metals are malleable, means you can bend them into different shapes, and you can make wires out of them. Copper wires, as an example. They are good conductors of electricity and heat, hence why most of your kitchenware are made of metals, and all electrical wires are made of metals as well. Some HDMI cables now have gold in them because people believe that gold is a better conductor than copper. They're shiny, hence why we're using them in jewelry. They have low ionization energy and low electronegativity. Ionization energy is the energy needed to remove electrons, while electronegativity is the attraction of electrons. We talked about this actually. We didn't specifically talk about this, but let me discuss what ionization energy and electronegativity are. So we talked about how metals like to lose electrons because they only have one or very few valence electrons. So they like to lose those to achieve chemical stability. The energy needed to remove those electrons, those valence electrons, is very low. Hence why metals have low ionization energy. And they have, so that's why they have low ionization energy. The energy needed to remove their valence electrons is very, very low. Again, the energy needed to remove their valence electrons is very low. Now, electronegativity, it's also low. What is electronegativity? Electronegativity is the will to gain electrons, is the element's ability to gain electrons, or is the element's interest in gaining electrons. So, take for example francium. If francium wants to achieve chemical stability, it would have to gain 7 more electrons to achieve chemical stability and have 8 valence electrons in its last shell. That's just way too much work for francium. Francium would much rather lose that valence electron that it has so that it can transition into a lower energy state or a lower shell and achieve chemical stability. It's much easier for francium to lose 1 electron and achieve chemical stability than it is to gain 7 more electrons to achieve chemical stability. The closer you get to francium, the more likely your electronegativity will be lower and your ionization energy would be lower, and you're more likely going to have more and more metallic properties, meaning that you're more likely going to be more solid, more dense, shinier, and have a higher melting point and a higher boiling point. Okay? So this is simply, I refer to it as the low for low ionization energy, low electronegativity, left loser, because it likes to lose electrons. It's on the left side of the periodic table, it's on the lower left of the periodic table, and it likes to lose electrons. On the other hand, you have fluorine over here. We're not going to talk about the noble gases because they don't like to lose, they don't like to gain, so we're going to skip those. We're going to talk about the fluorine. Here we have the high for high ionization energy, high for high electronegativity, gainer. It likes to gain electrons. Okay, the closer you get to fluorine, the more likely you're going to have non-metallic properties. Now, non-metallic properties are the exact opposite of metallic properties. So if metals have very high melting points, non-metals would have very low melting points and very low boiling points, hence why most of the non-metals are actually gases. Okay, remember, hydrogen likes to have fun with chlorine and group 18. We got a bunch of gases here already. It's very important to notice that in group 17, we actually have 3 different phases of matter. We have the gases, and as we keep going lower, we keep going to the bottom of the periodic table. Hence, again, we go to the lower left. If we go to the bottom or we go to the left of the periodic table, we're going to become more and more metallic. So fluorine and chlorine are gases. Bromine is a liquid. Iodine is actually a solid at STP. So the intermolecular forces are actually increasing inside these atoms, inside these elements. So it's becoming more and more solid. It's becoming more like a metal as we keep going further and further down the periodic table. And if we keep going to the left as well, it becomes the elements become more like metals. You can actually, if you're confused a little bit and you kind of don't really want to use this trend, and let's say you get something that's a little confusing, you don't know if this one is more metallic or this one is more metallic. So, well, they're both non-metals, but which one would have like less non-metallic properties? You can look at table S, and you'll see each element's electronegativity value. So if I was to compare, for example, niobium with molybdenum, I see that niobium has a higher electronegativity. Molybdenum has a higher electronegativity than niobium. So therefore, molybdenum is more likely to attract electrons and behave as a non-metal, while niobium is more likely to not attract electrons and behave more like a metal. However, both of them, you gotta look at their position on the periodic table. So if they were on the left side of the periodic table, obviously they're metals, but one is more metallic than the other. And if they were on the right side of the periodic table, obviously they're non-metals, and one would be more non-metallic than the other. Okay. Going back to here, let's see. Here we talked about, we didn't talk about this, so let's read this. Okay, let's take a look at table J. So here's table J. This is hydrogen. All these metals here are less active than hydrogen. So if you had hydrogen combined with an acid, such as one of these metals combined with an acid, such as HCl, let's say Ag plus HCl, you're not going to get any reaction. But let's say you had a metal that's more active than hydrogen reacting with HCl. Let's say take, for example, titanium. Titanium is more, let me just erase this, make it more clear. Titanium is more active than hydrogen, so titanium will come and replace hydrogen, knock it off. Hydrogen will walk away as a hydrogen gas, and titanium will take its place to make TiCl plus H2. Okay, so titanium chloride plus hydrogen gas, and hydrogen gas is very flammable. This will also work the other way around. Let's say you had HCl and you reacted that with fluorine. Fluorine here is more active than chlorine, so fluorine will come and knock off chlorine to give you HF, and then chlorine will come right off. Okay, so this is how we can use table J. All the acids are actually on table K. Here they are. We'll talk more in depth about acids later on. So here are a bunch of acids. And here are a bunch of bases. We'll talk more about that later. Okay. We talked about all of this. We talked about how francium is the most metallic metal of all times. Let's talk a little bit about the names of the periodic table groups. So, here we have the alkali metals group. This is the alkaline earth metal group. This is the noble gases group. This is the halogens group. Okay, alkali metals, group number 1, this whole group here, and alkaline earth metals are the most active metals of all times. A lot of times we actually keep these in oil because we don't want them to react with any other elements in the atmosphere. They're very reactive. If sodium touches water, it explodes and turns into fire. So these are highly reactive. Again, we keep them in dark glass oil containers. If you react any of these alkali metals or alkaline earth metals with group 17 elements, you'll make salts. The halogen group, you'll make salts. For example, Na, when it reacts with chlorine, you'll make the common table salt, sodium chloride. All of these other elements here in the valley, I like to call this the first tower and this is the second tower. So here, all the elements in the valley, if you put them in water, you'll make colorful solutions. So let me highlight these for you. If you put these in water, you'll make colorful solutions. For example, if you put copper in water, you'll make a greenish solution. If you put iron in water, you'll make a brownish solution. Okay, another thing you should notice about these is that they tend to have multiple different oxidation numbers. In other words, they have multiple different charges. So here we have iron +2 +3, copper +1 +2. If these atoms react with other elements, for example, they say they react with oxygen. When copper reacts with oxygen, it can form 2 different compounds. It can become CuO, copper 2 oxide, and it could also become Cu2O, copper 1 oxide, depending on how many electrons it loses. We'll talk more about how we got CuO and Cu2O later on when we get to bonding and writing formulas in other videos. Okay, going back here. We talked about all of this. We talked about all of this. Metalloids, we didn't really talk much about it, but silicon is the most common metalloid out there that is used in computer chips. So silicon is a semiconductor. Again, it's not a metal, it's not a non-metal. It behaves both as a metal and a non-metal. So it's not really a good conductor, it's not a bad conductor, it's a semiconductor. So when we use it in computer chips, we prevent power surges. When combined chemically, metals and nonmetals form ionic compounds. So here's an example of NaCl, an ionic compound. Na, metal, Cl, nonmetal. When you put a metal with a nonmetal, you make an ionic compound. When you put that ionic compound in water, the ionic compound will dissociate in this fashion. So the negative chlorine will attract to the positive hydrogen, while the positive sodium will attract to the negative oxygen. Here we have a dissociation of the sodium chloride, and because it dissociates in water, it will help carry electrical charge from one section to the next to the next. So that's why salt water is actually a good conductor of electricity. Here's some information here that you can read for yourself. And now I think I covered everything for properties of metals and periodic table trends. Now I'm going to go back and show you the questions. Here they are. You can pause the video and try to answer these questions. There are a total of 7. Determine whether the following statements are true or false. Thank you.